So thank you very much. Yeah, maybe I can a bit start with where we had the first keynote where Misha said, well, PDEs are the language of nature. Well, for us in system dynamics, it would be actually, let's say, the Hamiltonian formulation of the classical physics, because this yields us automatically distributed differential equations. And if we actually take our physical systems and apply that, we actually get a nice ODE for the system that has very nice properties. If it's derived from the physics, you will know that you can solve this ODE, because we do not have a blue screen in the world. So, I mean, maybe I have once at the end of my life a blue screen, but so we can solve. So I can make an a priori statement on the solvability. It's a physical system. So I have one problem there. Physics, if we model physics, we get physics. That's the problem. So, and physics has high frequencies. And so you can see we have always to cover a huge broadness and frequencies from power electronics going here for the small signal response in the megahertz. And then maybe you want to do complete analysis, you're choosing grid code compliance in the hertz, maybe, and then maybe you want to evaluate whole days or whole years. So you have these huge frequencies you have to span. Goes for thermofluid as well. Shock waves are often in tens of kilohertz. And then you have the heat exchangers to operate within minutes. And for robotics too, you have a small macro motion, and then you hit, and you have a shock wave going through your arm in the kilohertz. And this is a problem because if you look what happened with the compute, pretty much at that time where Modelica really got popular, the clock speeds stalled, which is the most useful thing if you want to compute high frequencies. It's the natural thing. And actually, if you look at the more modern and prevalent compute architectures, the GPUs, there is a tendency to even lower the frequency. And that trend will not change. There are physical reasons for that. Actually, lowering the frequency is often a big. It's often the easiest measures to solve your problems on the compute device in terms of energy and integration. So that is, of course, a problem. So it's actually also an opportunity for us in Modelica, because you cannot model everything with this ODE approach. And people hence start to idealize this. And then you end up with a DIE. So one thing is very important to understand. I want to make that clear. Often this idealization is an over-idealization, which means you idealize so strong that the information how to solve is idealized away. It's gone. And what is important is you have to really understand it as an information theoretical problem, because it means no algorithm can save you. If the information is gone, it's gone. There's no magic button that will save you. You can start guessing, and it may work for small systems, but it will never lead to a scalable solution. So often what is, for instance, often done is you couple potential energies in physics directly, which is not what physics is doing, but it's a very common measure of idealization. And this means, well, we have these DIEs, that's wonderful, that's our Modelica world. We can achieve the job. We have excellent means, if you are a good modeler, to suppress the frequencies. You can get rid of them completely. You can transform a complete algebraic system. That's all fine. But you can make no a priori statement on the solvability, and you need to flatten it. You need to look at the whole system. So you need a global analysis. Here you can make a local analysis. You can create modular code. Here you have to collect everything. You need to model. And the reason for that is simply the process of idealization. And again, this is an information theoretical point. It doesn't matter what tool, it doesn't matter what language, that is simply very general. Okay, so there is this is not a favorable trade-off situation we are in. I mean, it's not good having to give up local analysis and a priori statements just to suppress your frequency. It's not satisfying. So I walked through this valley. Isn't there something in between, which is maybe a good compromise? And I found this linear implicit equilibrium dynamics, which I will explain in a minute. And this still gives you the option for local analysis. So you can create modular code. You can still make an a priori statement on the solvability, and you have reasonable means to suppress the frequency. Not perfect, not you can do better with VIEs, but reasonable for many, many applications. Okay, so this is the dry math. Basically, what I mean, this is a class where after you do where you can decompose your DAE into an explicit part for all the nonlinear stuff. So you can have nonlinear parts in your DAE, but they need to be put in an LU form so that you can compute one thing after the other. And you are allowed then to have a linear equation system at the end. And this is actually to be constructed in such a way that it's guaranteed to be regular. In the process to get to this form, you might have to apply once a differential index reduction. So these are typically index 2 systems, to say so. Point is, basically, I make the claim, I have no proof, maybe someone wants to do the proof, that basically, I think maybe even relativistic, but certainly non-relativistic systems where you have a proper dimensioning of your kinetic energy, so where it is sufficiently high dimensioned, then you can find a linear implicit equilibrium dynamics for such a system. Okay, well, this is very, very dry and looks totally unpractical. But in reality, it turns out to work very well because the thermofluid stream library is designed around this concept with the exception of the media models. That's at the moment the only breaking point because we didn't want to change that. And to explain, so the blue part, the explicit part would be that you compute downstream all your evil nonlinear thermodynamic computations from source to sink over the junctions. The linear equation system would then care about bringing the kinetic to take the resulting gradients and bring the inertias of the different fluids, so bring the kinetic energy of the fluids in balance, so towards an equilibrium. Then later, so this is where it started. No, sorry, this is wrong direction. And then later I found out, oh, okay, actually, you can find an exact similar formulation for mechanics as well. Again, you take the blue part, which is simply the geometry of the motion. This is the nonlinear part of your mechanical stuff that you have. And then you can form a linear implicit part to transfer the kinetic energy. And you can even do this in such a nice way that you can manipulate the frequencies. So you can formulate very stiff contacts, for instance, without having to manipulate your spring damper constants. So here, that's an example with an explicit solver due to the eigenvalue manipulation. I showed this last conference already, but it's nice, so I show it again. So you see here the slip and the ball. This is stick slip behavior that you can do. And this is completely with this lead equation formulism and completely with explicit solvers. Very easy then to simulate. Then in Boston, when Chris and Scott enabled a nice sabbatical for me, thank you again, I had time to care about tricky stuff. So I looked also for a form for controlled energy flows. This is a very frequent thing that many people do, actually. Often when you model electrics, the natural behavior is actually suppressed by the strong control dominance you have. So actually, for many analysis, you actually want to have the behavior of the pseudo-control system for analysis of energy consumption, etc. So again, here you can do an explicit nonlinear computation for your energy flow regarding the efficiency, etc., blah, blah, blah. And then you have a linear implicit control scheme that syncs all the components and reaches the desired equilibrium if it can be reached. Again, very, very robust. So these three libraries, sorry. are already very useful. For instance, you can model a complete electric car with this. And you can also model an aircraft with energy systems with it. Up to a certain level, you can do. And what I found also Marek's work on the chemical 2.0, so he also tried to apply this concept. So maybe I have to look at now this library. It's really fantastic. Even chemical computations can be brought into this light scheme. So we start to have actually a very useful set of practical object-oriented libraries with this. And to enable this, we always need this, we go away from these classic pairs that we know, and we go to triplets. So the idea is you have always a carrier signal. So this is the violin player. And then we have our pair of effort and flow that's dancing to that. And we can now, again, we can make an assumption of causality for the sake of code generation. That doesn't mean it's causal. But we can assume that the potential has the same causality as the carrier signal, and we'll assume the flow has the reverse causality of it. Very easy. And then basically you have components with completely causal connectors, and then it's pretty clear that you can generate code for them. And here to show practical examples, so this is for a planar mechanical library model to this. And you see here, this is the carrier signal, then followed by the potential, and followed by the flow. And you see always the reversal that can be taken. So you can then very naturally model a body component that looks nice. And I show a bit more of a complicated example of the revolute joint that would be a degree of freedom. And what I need to introduce here now is we need to tear these linear equation systems. And I can introduce this in Modelica without any special language features by simply making such a model linear response with an input and an output. I could also call it a block. And just saying that the residual is 0, we have to make this annotation that is for the local check. And that is basically the way to formulate a theory so that a normal Modelica compiler just normally processes it. So you don't have to change anything at the existing tools. That will be understood. And then you can go ahead and model your revolute joint like this. Okay, and if you have this, if you adhere to the subclass, you suddenly have now completely different compile paths to your variability. So you can basically bypass the flattening. You don't have to flatten the model anymore. You can do a component-wise compilation, and you can generate object-oriented simulation code. And this is very useful for a number of reasons. So first of all, it's getting way easier to simulate large models because you have much fewer code in reality. You can actually also start to simulate variable structure systems better because you could change these components at runtime. I mean, that's a different question, not within Modelica. You cannot express it within Modelica, but you can use the code to help yourself. You can way better integrate that code into simulation engines. So for instance, if you say, I'm wanting to develop a computer game, and I actually want to have equations for my main agent models, but in the end, then I want to tightly integrate that. You can generate the code, take the object-oriented code, place it into your engine. If you are an able programmer, you can do that. We have similar applications within VLR that people like to do agent rover simulations. The people tell me, if you give us the C++ code, we can do the rest. I mean, they're able programmers. If you give them the code, they're fine. And one thing important is also, this would be also free of any ambiguity. So for instance, funnily, you made this tool to remove the ambiguity. In this form, you wouldn't even have them. The states and the initialization would be clear. Oh, that would be also nice. And I hope, so I will do this now for the CPUs, but I think for GPUs, we need kernel functions. So modular code is also a prerequisite to get effective code for the GPUs. It's, of course, a question to what degree you want to flatten, but well. So I think that is very attractive from the point of from direction. Okay, at the time. Okay. Yeah, so this is, for instance, how such a code could look like. You can create a class, and you can create very simple evaluation functions. And then there's some meta information that can tell the simulator when to call what function. I don't go into details, but you can generate this code. I've made some tests in the past. You've seen the slides maybe. So if you create such object-oriented code, how would you scale? These are comparisons with a commercial tool here. And gray is open Modelica, and the light systems, the simulation code here. And you see I can, on my laptop here, on my device, I could reach 800 million equations without problem. And if you have a larger device on a CPU, you can go easily into the billions of equations. You need far less memory. You compute most of the stuff on the stack, so you don't need to allocate on the heap. You can do the computation on the stack. Speed is okay, actually, because the way the linear system is solved, it is a little less performant for small systems. And if the system gets very large, for some reason, the difference completely vanishes. So this shows the potential that you get if you generate modular code. Yeah, okay, how to do that? Now, one may be tempted to try to do a one-to-one translation between Modelica structures somehow, and then, for instance, you target in C++ or C. And that's not a good idea to try to do that, because Modelica has never been built for that. And the train has left. Well, okay, yeah, maybe, okay. Well, we can have a discussion. But it's very, very tough. It's very, maybe if you want to do it, it's very tough, because you basically, a model in Modelica is a model template. So you can have your conditional connectors, you can have your redeclar replaceable. So that makes it very, very tough, because actually it's a template. Not so instead, what is a good way, and I think actually very good for many tools to adapt, because it's not so difficult to adapt, is, well, I'm just writing currently the instantiation process. And this is basically, if you do it correctly in Modelica, an interpreter. It's much closer to an interpretation process than to what a compiler does. So, because you wait until you have to generate a complete instance, and then you do all the work. And then you start, instead of flattening the thing, you just start to generate the code for the individual instances. So you instantiate a model, you make code. Instantiate model, code. So you generate an awful lot of code, most of it being redundant. But who the fuck cares? We'll just make a filter afterwards and see, okay, do I have this piece of code already? Oh yeah, I have it. Throw it away, reference the old code. This is extremely stupid, but it works actually extremely well. It's stupid, but it does work. It's not a nice design, but it works. And you have a huge amount of code compression by this. And you get a modular code. So that's totally fine to do it this way. And I think this is actually very easy for many existing tools to adapt, because they already have often something like that. Often they have an intermediate non-flattened form. So you would just need to make the code generation based on that and then apply a filter. It's stupid, but it does work. Okay, yeah, I'm currently writing that. So there's a console program. Okay, because of the computer, I cannot now demonstrate it. Yeah, but basically you can take such a thing. The program is written like it does, that it runs continuously in the background. So you can take your Modelica program in the future, hopefully. So the idea is we can reuse the IDEs. Oh, I have to leave. Great, thank you, Martin. And this will just work in the background and compile every time you save. It will just translate it into code. It goes super quick. Yeah. So it's actually not so complex. So you see at the moment, I'm at about 6,000 lines of code, a completely standalone C++ implementation. So I think it will be very performant. Yeah. And I think it's a good, so, okay, conclusions. I should go to the conclusions. No, wait, very quickly. Okay, hope is with this class we can achieve better scalability on CPUs, and hopefully it will be also well suited for GPUs. Proof is of course not there yet. I think also, yeah, the rest I mentioned. It's a great chance also to shed complexity in the language in a way that we don't have to harm the actual Modelica, because we can leave that, but we can just define this subclass nicely. And one of the reasons why I started the implementation is that only by implementing you realize what are the real sources of the complexity. They're sometimes not very intuitive and well hidden. Okay, and so the main aim will be actually to define the subclass, and to do this I need to finish my implementation, because that's the only really proper way to really prove it and show that you have the main fix. Okay, and I will make my work then available open source. I think we have nice potential here. So my answer is beautiful results. But of course, if you take a Modelican person, the only thing he sees is equation. So there's a blue equation. Equation. Okay.